Hi, calculus students. These notes are on something called Riemann sums. And Riemann sums are a formal name for something that we've been doing for the last couple days in class, which is we've been approximating the area under a curve by finding the area of little rectangles. So I'm just going to kind of put up top what the big idea here is, which is exactly what I just said. So we can approximate the area under a continuous curve on some, we'll say on some interval. So by interval, I mean like a range of x values or independent variables. And how do we approximate this? We can say by adding the areas of small fitted rectangles. Okay, and so I'm going to show you 3 different ways of doing this, and the big idea here is that this relates to the idea of an integral, meaning the area and the precise area under a curve. We started by looking at this in terms of velocity functions, the area under a velocity curve meaning the displacement or a change in position, but we're kind of generalizing now to any function. How can we calculate the area under the curve? So we're going to start with the function f of x. We're going to start with this. We're going to actually use the same function every single time. And I actually know what the formula is for this function. It is f of x equals 1/3 x squared plus 2x plus 5. And for all, I'm going to show you how to do these 3 different ways. But for all 3, we'd like to approximate the area under the curve, and we're going to do it on the interval from 1 to 7. So we'll say on 1 to 7, and I'm going to choose that we're going to use 3 rectangles. And the way we say this is we say like using n equals 3 subintervals. Okay, n equals 3 subintervals. So the first way we're going to do this is what's called a left endpoint approximation. And before we begin, I'm actually going to put a little table of values off to the side that we're going to refer back to throughout the process, because we're going to need to pull specific y values off the graph as we go, and it's just going to be quicker if we can just reference them over here. And the way I got these values was by plugging in the f of x formula into the y equals in the graphing calculator, and then just looking at the table and getting the y values for each x value. So I've already kind of pulled those, so we're just going to record them for the sake of time. And I'm just going to do everything from 1 to 7. We may not use all of them this first round, but eventually we are going to use them all. So at 1, it's 6.67, and I'm rounding my thirds to the 0.67. At 2, it's 7.67. At 3, it's 8. 4, it's again 7.67, and again 6.67 at 5. At 6, it is 5, and at 7, it is 2.67. So again, just kind of, you might want to pause. You can write all those down, but we're just going to be referring back to that as we visualize what length we're using for our rectangle and what x value is determining that height. Okay, so the idea of the left endpoint on 3 subintervals. So the first of all is this idea that if we have 3 subintervals, and I'm going to show you kind of a visual way of thinking about this. So I'm going to draw 3 lines. And we know that these 3 lines are kind of representing the bases of my 3 subintervals. So I'm going to start with a 1 here and a 7 here, because I know that I'm doing it from 1 to 7. And I need to figure out, like, well, what x values go in these other two spots if I want to use a subinterval, if I want to use a total of 3 subintervals. And so we call that value the change in t, like how wide do I need to make one subinterval is the change in t. You see, that's always going to equal, well, what's the length of the subinterval? So like b minus a, which would be like 7, in our case 7 minus 1, divided by the total n number of subintervals. So in our case it would be 7 minus 1 divided by 3, right? Because I want 3 subintervals and the difference between 7 and 1 is 6. So I'm going to end up wanting a width of 2 for each subinterval. And maybe you could have done that in your head, but if you're ever confused, you can use that formula. So if my each width is 2, that means this next number should be a 3, then a 5, then a 7. And maybe you could have also kind of seen that by kind of sectioning out your subintervals. Okay, so I'm just kind of like drawing those vertical lines in at each place. Now, the idea of the left endpoint means I'm going to cap off each of these rectangles using the left side of the rectangle. So like for the first rectangle, it goes from 1 to 3. So I want to cap it off at 1. So on my graph, what that looks like is tracing up at x equals 1, tracing up to the y value, and capping off my rectangle. So for the second rectangle, I want to use 3 to cap it off, which looks like this. Then for the last one, I'd like to use 5. So the idea of this, this is like a visual kind of way to organize the information, but it helps you kind of visualize what x value you want to use for each rectangle, where each line represents one of the rectangles. So then for my last one, I'm using 5. So I'm tracing up on 5 to where it hits the graph, and then drawing the horizontal line the rest of the subinterval. So now that I have my rectangles drawn, I have to think about how do I calculate the area of each of them. Well, it's going to be the width of my subinterval 2 times the height for each rectangle. So for the first one, I want the height at 1, which is, if I look at my table, 6.67. So I'm actually going to write that in up top. I'm going to use a different color. So I know it's 6.67. Then for the second rectangle, I'm capping it off with a 3, so I want to pull the value at 3, which is 8. For the third one, I'm capping it off at 5, so I want to use the value at 5, which is 6.67 again. And now the idea is if I actually want to do the calculation, I need to do each of these times the width of the subinterval to get the area of each rectangle and add them up. So since the width of each subinterval is 2 each time, I could just sum them up and then multiply by 2 at the end, which is quicker. So that's what I'm going to do. So I'm doing 6.67 plus 8 plus 6.67, but all multiplied by 2, and this ends up being 42.68. So that would be a left endpoint approximation. The next one I'm going to do is what's called a right endpoint approximation. So for this one, again, I'm still using the same number of subintervals. So 1, 2, 3, from 1 to 7, and I'm dividing them up in the same way. So it's going to kind of start the same. But the place at which I cap them off is now going to be the right endpoint instead of the left endpoint. So what that's going to look like, well, in my visual, that means kind of like drawing up the right side of each segment of the visual aid. On my graph, that looks like, okay, for the first rectangle from 1 to 3, I want to cap it using the y value at 3. For the second one, I want to cap it using the y value at 5. So again, I'm like tracing up from 5 to where it hits the graph and then just capping that off at that y value. The last one, I'm using the y value at 7. So it looks like that. So now, what are those actual values? Like, what's the areas I need to calculate? And this little visual aid is going to help me. So if I'm using it in conjunction with the table over here, then I know I need the height for the first rectangle at 3, which is 8 from the table. For the second one, I need the height at 5. For the third one, I need the height at 7. And so now I know I have to do the width of my subinterval 2 times the sum. And again, this is this 2 out here is basically just like the distributive property of I could just multiply by 2 at the end instead of multiplying each of them by 2. And if you type this into your calculator, it ends up being 34.68. Okay, so notice like we have actually done both of these two in class. We've done a left endpoint and a right endpoint. We just haven't called them that. This next one is going to be slightly different. It is going to be called a midpoint approximation. And the idea of a midpoint approximation is it's using the center point between the two endpoints of a subinterval. So if I draw my little lines again, for 1, 3, 5, and 7, instead of using 1 or 3, I'm going to use the value right in between them. So what's the value between 1 and 3? It's going to be 2. What's the value between 3 and 5? It's going to be 4. What's the value between 5 and 7? It's going to be 6. So those are the x values whose heights I'm going to use to cap off each rectangle. So I'm just dividing up my subintervals first. And then the idea should be, okay, from 1 to 3, I'm using 2. So if I trace up to 2, then I'm capping it off at that midpoint. From 3 to 5, I'm using 4, so I'm capping it off that midpoint right there. And then from between 5 and 7, I'm capping it off with a value at 6. And the idea of doing a midpoint versus one of the other two is it looks like it's going to be a more precise answer, because there's some parts that there's like some little parts that are overestimating, but there's also some little parts that are under. Excuse me. Versus in the other two, if we just slide up, we had much larger kind of chunks missing that we were under approximating or over approximating. So that leads me to think that maybe this is like a vast underestimation, this is a vast overestimation, but the midpoint might be more precise. So now that we kind of have thought more conceptually about that, let's actually pull some more values. So now I actually need to find the areas of each of these. So I'm going to look back at my table. So I need the value at 2, which is 7.67. I need the value at 4, which is also 7.67. And I need the value at 6, which is 5. So now that I've pulled those, my subinterval width hasn't changed. Each rectangle still has a width of 2. So it's still going to be 2 times the sum of those three numbers, 7.67 plus another 7.67 plus 5 times all times 2, and this ends up being 40.68. And notice like 40.68 is right in between, or not exactly in between, but it's in between the original 42.68 we got with the left endpoint and the 34.68 that we got with the right endpoint. So it leads us to believe maybe the midpoint might be a better approximation. And there's also something called a trapezoidal approximation, which would actually calculate the area of a trapezoid between the two endpoints, but we're not going to focus on that this year. And the last kind of thing I want to get you guys to put down into your notes is something we figured out in class, which is that the more rectangles you use, the better the approximation will be. So we'll say the more rectangles, also called n subintervals, you use, the better the approximation will be. Okay, so now if you flip over to the back, there are 2 practice problems for you to try. One is based on a graph, but it also gives you an equation. So just a preview. So you're kind of interpreting what type this sum looks like. Is it a left, right, or midpoint approximation? And then using this formula to derive those y values that you need. And you could put this into y equals on a graphing calculator, or you could also use Desmos. And the second one is purely based on a table, but we can still do the same idea if we kind of use our visual aid. You don't necessarily need a graph to do number 2. Okay, so do the best that you can on that, and we'll be discussing it in class.